Bacteria and other microorganisms have the ability to form biofilms on inert support media. Can we use these biofilm systems for sewage treatment? Attachment of microbes to inert support material is a cost-effective way to retain the bioactivity in the reactor. On the other hand, the space occupied by the support material cannot be used for bioconversion. In this lecture we will discuss the various design and operational aspects of trickling filters for sewage treatment. A trickling filter is a low-loaded engineered system that makes use of the immobilization capacity of microorganisms on solid support material. Traditionally, a trickling filter is 2 to 4 meters high and is filled with rocks that are mounted on a perforated floor. A trickling filter is a biological reactor and, in fact, replaces the aeration tank in an activated sludge system. Since the biomass is retained in the filter, the sludge has a long residence time and thus is also stabilized in the filter. Therefore, much lower quantities of sludge are being produced in trickling filters compared to activated sludge processes. In a trickling filter, the sewage is equally distributed over the support material at the top part of the filter. In round trickling filter, this is generally done by rotating arms. During passage of the sewage towards the bottom floor, bacteria mineralize the organic matter. Since the conversion is an aerobic process, adequate air supply is of utmost importance. The drain water is collected and conveyed to a clarifier and subsequently discharged. The biomass growing in a trickling filter is very diverse and consists of bacteria, protozoa, algae, worms, etc. By using stones as filling material, a large part of the filter bed cannot be used for bioconversion. Alternatively, very porous plastic packing material can be used in the so-called high rate or tower trickling filter. These filters have a height of about 8 to 10 meters. Since the bioconversion rate is much higher, oxygen supply is much more critical in these filters. If convective aeration is non-sufficient, high-rate trickling filters might be equipped with additional blowers. The biofilm, or biological skin, is about 1 to 3 mm in thickness. The biofilm is a layer of microorganisms attached to the inert support material. The biofilm has a slimy appearance and consists of multiple layers in which both aerobic and anaerobic conditions appear. In addition to living organisms, also cell remainders and entrapped solids are part of the biofilm. How do these different layers form? The air oxygen diffuses in the water layer that trickles down the biofilm. The aerobic organisms use the solubilized oxygen and mineralize the organic matter to CO2, water, ammonium, phosphates and sulfides. The deeper layers of the biofilm, which are close to the support material, are now depleted from oxygen and are anaerobic. Note that the formed reduced compounds such as ammonium and sulfide are odorous. Also deeper in the bed towards the filter floor, oxygen can be limited owing to the high biological activity at the top. Proper venting or air supply is therefore of utmost importance in the trickling filter. However, under low to moderate loading conditions, also the bacteria that oxidize sulfides to sulfate and ammonium to nitrite or nitrate may develop in the biofilms of the filter, leading to full BOD removal. Adequate oxygen supply is considered the most important aspect of a trickling filter design for sewage treatment. The transport of oxygen from the air to the liquid film is driven by passive diffusion, thus by the oxygen consumption rate and the temperature. In fact, the temperature difference between the sewage and the surrounding air is a driver for convective airflow through the filter bed. If the air temperature is higher than the sewage temperature, then an airflow from outside the filter to inside the filter bed is created. This airflow is based on a decreasing air volume when the air comes into contact with the cold sewage flow. The airflow takes possible odorous volatile compounds in its downward flow. The odorous compounds are subsequently oxidized in the deeper parts of the bed. In reverse situations, so when the airflow is colder than the sewage, an upward airflow can be expected and thus a more smelly trickling filter. An adequate airflow is already obtained with very little temperature differences. A difference of 4 degrees Celsius already causes an airflow of 18 cubic meter per square meter surface per hour, whereas only a flow of 1 to 2 cubic meter per square meter per hour is needed. When the temperature differences are less than 1.9 degrees Celsius, no net fluxes are observed. In order to enhance the chimney effect, the walls of a trickling filter are generally closed. What are now the most important aspects for operating a trickling filter? First, the wastewater concentration and composition. 2. Type of filter material. 3. The formation of biofilms to effectively retain the biomass. 4. Oxygen supply to the biofilm and through the filter bed. 5. Sludge growth and biofilm thickness. Excessive sludge growth may lead to partial clogging of the filter bed and a loss of bioconversion capacity. 6. Biomass stratification. Heterotrophic bacteria oxidizing carbon grow much faster than nitrifiers. Therefore, at the top part of the filter bed, heterotrophs may proliferate, whereas nitrifiers might be more abundant at the bottom part, where the formed ammonium is oxidized to nitrite and nitrate. Nitrifiers will only grow when oxygen is not limited in the deeper parts of the bed. 7. The applied BOD loading will immediately impact the treatment performance of the trickling filter. The higher the BOD load, the more sludge will grow and the more crucial the oxygen supply will be. In addition, at a high BOD load it will be more difficult to also oxidize the formed ammonium. 8. Biofilm growth can also be controlled by applying effluent recirculation. A higher hydraulic shear limits the biofilm growth and minimizes clogging. In addition, effluent recirculation also creates a hydraulic buffer. And 9. Since trickling filters are dependent on biofilm formation, the best season to start up a filter is spring or summer. The inner support of filter material can be anything suitable for attached growth. Best performance is obtained with material that has a high specific surface per cubic meter of volume, has a high overall porosity to prevent flow channeling in the bed. Moreover, the material should be biochemically inert and should be rigid. 4th, should have a low specific weight, and 5th, should be low cost. Traditionally, lava rocks are used. These are 5 to 8 cm of stones with specific surface of 80 square meter per cubic meter. The wet weight is 2000 kg per cubic meter and the free space in the bed is about 40%. Trickling filters with this filling material have a height of 2 to 2.5 meter. High-rate trickling filters are filled with plastic with a specific surface of 100 to 230 square meter per cubic meter. The free space in the bed is 90 to 98% and the wet weight is only 250 to 400 kg per cube. So, the average height of such trickling filter can be 8 to 10 meters. Proper water distribution, or wetting the biofilms, is considered crucial. Most trickling filters are equipped with a rotating arm, which rotates by water pressure. In order to achieve this, the orifices are positioned only at one side of the arm. The length of the arms are generally not more than 40 to 45 meters. Alternatively, a fixed system is constructed in which the filter bed surface is equally wetted. Floor perforations are generally 15 to 20% of the total surface and equally distributed to prevent preferential flows. Operation performance and functionality of a trickling filter is determined by the applied BOD loading, expressed as kilogram BOD per cubic meter volume per day. In a high-loaded system of 0.7 to 1 kg BOD per cubic meter per day, only organic BOD will be oxidized. At higher loadings, the oxidation is incomplete and the efficiency rapidly drops. The high loading causes high biomass growth. If the high BOD load is accompanied by a high hydraulic load, then the sludge will be rinsed from the system. Otherwise, clogging may appear. In a high-loaded trickling filter, about 0.6 to 1 kg dry solids of sludge per kilogram BOD removed will be produced. At intermediate loading of 0.3 to 0.5 kg BOD per cubic meter per day, full BOD oxidation will occur and maybe also part of the reduced N forms will be oxidized to nitrate. Full nitrogen oxidation can only be expected at low loading rates of about 0.1 to 0.2 kg BOD per cubic meter per day. If the hydraulic load is insufficient for proper distribution or biofilm control, often effluent recirculation is applied. Note that in low-loaded systems, much less sludge is being produced, about 0.3 to 0.5 kg dry solids per kilogram BOD removed. A trickling filter is generally preceded by a primary clarifier to prevent the accumulation of solids and fats onto the filter bed. Excess sludge leaves the filter with the effluent and is retained in a secondary clarifier. As mentioned, the produced sludge is already partly stabilized, dependent on the applied BOD loading rate. From the secondary clarifier, often recycling is performed. Recycling can be performed by pumping the secondary sludge with the nitrified effluent to the primary clarifier. The overall excess sludge is then withdrawn from the primary clarifier for further treatment. The oxidized and nitrified effluent facilitates odor control in the primary clarifier and the trickling filter. When connected to a gravity sewer, the primary clarifier is preceded by an influent reception basin. In such case, the recycled secondary sludge will be added to the reception basin for enhanced odor control. Additionally, the nitrified and clarified effluent might be directly recycled to the trickling filter to increase the hydraulic loading to the system and to prevent volatile odorous compounds escaping the filter system. Reduced volatile compounds such as sulfides are then oxidized by nitrate. Effluent recirculation generally leads to improved process performance of the trickling filter. Trickling filters are considered a cost-effective solution for particularly low sewage flows when only BOD removal is required. The low operational cost makes them attractive for application in developing countries. On the other hand, trickling filters get easily overloaded when sewage flows increase. We then have to change to suspended growth systems, as will be explained in the coming lectures. So, stay tuned and keep following our course.